Can anyone confirm? Am I audible and my screen is visible or not?
Yes, sir.
Okay, the screen is visible.
Hmm.
Okay, then let's start. Good evening, everyone. My name is Chandan Kumar Gupta. I am a Prime Minister Research Fellow in Department of Mathematics, IIT Patna. I am your NPTEL TA for the course Introduction to Probability Theory and Statistics. This course is offered by Professor S. Dharmaraja. He is a professor in IIT Delhi. So this is the 10th week of a 12-week course. So up to the 9 week, we have completed about like introduction to probability theories. And in the last week, we have discussed about the statistics or introduction to statistics. Okay. So like, okay. So like in probability theory, we will discuss about the basics of probability, types of random variable, different kinds of random variable, Bayes theorem, uh, conditional probability, total law of probability, and we have also discussed about moments and inequalities, in which we have discussed about higher order moments, generating functions like moment generating function, probability generating function, characteristics function, etc. We have also discussed about the standard deviation, standard distributions such as different kind of discrete and continuous distributions like Poisson, binomial, Bernoulli, geometric, and negative binomial distributions. We have also discussed about different kinds of continuous distributions like normal, exponential, beta, gamma, etc. And in week 5, we have also discussed about like higher dimensional distribution. We have in which we have like discussed two or higher dimensional distributions, how to calculate. So how to calculate joint and marginal distributions, uh, how to calculate marginal distributions from the given joint distribution, and how can we claim the independence of two random variables. We have also discussed about different transformations of random variable, order statistics, and variance, covariance matrix, correlation, and regression analysis. And we've also like discussed about modes of convergence, law of large numbers, central limit theorems, and like in statistics part, we have discussed about descriptive statistics in the 9th week, that is in the last week. Descriptive statistics in which we have discussed about the measure of central tendency, measure of dispersion, measure of skewness, measure of kurtosis, coefficient of variations, and different kinds of plots to show these graphical presentation to show these datas. Okay. Also, we have discussed about in 9th week, we have discussed about some statistical distributions like chi-square distribution, or sampling distribution, in which we have discussed about like chi-square distribution, t distribution, f distribution, and some properties related to these distributions. So these are the topics we have covered so far in 9 weeks. Now we are in the 10th week of the 12-week course, and in this week we have like we will discuss about the estimation parts. Okay, so in week 10 we will discuss about like point and interval estimation. Okay, so like in point estimation, we will discuss about what is point estimation, the method of point estimations, and then interval estimations, like definitions of point estimations and the methods. point estimation, in which we have specifically discussed about method of moments estimator, and maximum likelihood estimation. And then we will discuss about interval estimation. So these are the topic in the 10th week. So let's start with some recap from the 10th week lectures. Log, like we will we are discussing statistic or statistical inference or point and interval estimation. So like what is a statistic? I am writing about statistic, not statistics. Statistics is the subject that we learn. Okay. And statistic, it is a function of sample values, actually. Function of sample values. We have also discussed in the last week, what is parameters? Parameter. These are the like function of population values. Okay, like population mean, population variance, population median are the parameters. Okay, and the sample mean, sample variance, these are the statistic. Okay, so through this, and these statistics are calculated with the help of the samples. Okay, like through the samples, we are creating some functions, and through these functions, uh, we infer regarding the population information. So that's why this function is called statistics. Okay, statistic. Okay, and this process of selecting a sample and using a functional form of those sample to infer about the parameter is called the estimation. Okay, so there is one more term like estimator. Okay, so estimator is also a statistic, actually, a particular type of statistics which is used to infer any information related to the population through the sample is called estimator. Okay, let me write like a particular type of statistic which is used to infer any information related to the population any information related to the population uh, through the sample, through the samples, then that statistic is called estimator. Okay, and a particular value, suppose a sample mean like is an estimator. Okay, for example, let me write, suppose like let we have considered x1, x2, xn are random samples. Okay, so these are random samples of size n. Okay, then any functional form which contains these x1, x2, and xn are statistic. Okay, And when we use that statistic to use to predict or to estimate any parameter or about any population values, then that statistic is called estimator. And when we have the numerical values of those random samples, then we have a particular value or instant value for that particular estimator, then that estimator is called estimates. Okay, the value of estimator at particular point is called estimates. Okay, like sample mean here. Okay, usually we denote it by x bar. Okay, so this is actually nothing but it is like summation xi n. Okay, summation over I from 1 to n and xi divided by the total number of samples. This is actually sample mean. So it is a function of the random samples x1, x2, and xn. Okay, and this sample mean is used. This sample mean is used to like estimate the population mean. Most of the time or all of the time actually, population mean. These sample mean is used to estimate the population mean. So that means population mean is a parameter, sample mean is a statistics. But here, since sample mean is used to estimate the parameter, that's why this sample mean or x bar is called a estimator. And suppose we have x1, x2, and xn numbers like 7, 5, 9, 12, something, then that particular value is called, when we solve this, that x bar equal to maybe 3.7, 9.2, maybe any value, then that value is called actually estimates. Okay, so particular value of an estimator is called an estimates. Okay, so now we have a point estimation and and interval estimation. So suppose if we get one value, okay, then when we estimate one value, then it is called a point estimates. Okay, like if we get or if we like one value as an when we use estimator and we get only one value, then it is called point estimator. Okay, and if we get a value in some range, then it is called interval estimate. Okay, actually, we use these in our day-to-day life. Like, for example, everyone is like staying somewhere. Okay, just see any trees or any poles or the width of that road or anything. Okay, or the height of the room. Okay, then if I like say, what is the height of the room you are currently living? Then you may say it is around 12 feet or 10 feet. If you give it one answer, then it is nothing but a point estimator. Okay, but you can also say that na, like it may be 10 to 12 feet. Then you are providing a ranges of values in which the height of the room lies. So this is nothing but the interval estimation. Okay, so we usually use these concepts in our day-to-day life, but not in that like standard format. But yes, we will like we have already used these things. Okay, and yes, also suppose I'm talking about my height and what is my height, and some people may guess 5'6", some people may guess 5'8". Okay, and since some people don't know about me, then they may say around 5 to 6 feet. Then in that case, uh, it is not sure that my height is 5'6" or 5'7". So there are some differences in the estimated value or the guess value and the actual value, the actual height. So that difference is called actually error or bias. Okay, so we can like use our estimation technique, and we are like trying that this estimates like converges to our true value. But it is not always true that we find the exact value or the exact estimate for that parameter. So we have different kinds of properties of the point estimations. Okay, so let's name them one by one and we will discuss those. Properties of point estimators. Okay, so there are many properties, some of which are like unbiased. The estimator should be unbiased, and like consistency. Okay, let me write first sufficiency. Efficiency, consistency, and sufficiency. These are some of the properties a good estimator has. Okay, if a estimator is good, then it must be like it is like unbiased, it is efficient than the other estimators, it is also consistent in nature, and it is sufficient. Okay, so let's discuss these properties one by one. The first one is like unbiased. So like a statistic, suppose we have a statistics tx. A statistics tx is said to be unbiased, is said to be unbiased for the function psi theta, okay, of unknown parameters, of unknown parameter theta, if like expected value of tx is nothing but psi of theta. Okay, so that means when we take samples or when we have estimators, then the expected value of those repeated sampling, okay, we repeat the samples and make the sample mean. For example, let me write as an example. Okay, so like the expected value of sample mean is nothing but the population mean. Okay, so that means like we have collected one sample and then take the sample mean. We have collected the other sample, then again calculate the sample mean. We draw the another sample, and this process is repeated. Then we have a different sample means at each, for each samples. Okay, then we take the average of those samples, and that average, the average of the average, okay, the average of the averages goes to the population mean. So this property is called unbiased property. Okay, so like sample mean is an unbiased estimator of a population mean, we can like say this. Since it is not always possible na, that the sample values equal to the population values. Okay, so like we have introduced a term biased. Okay, so bias is an estimator which is not unbiased. Okay, an estimator which is not unbiased is called a biased estimator. Okay, and usually this is like denoted as B. The estimator we have used is T, and the parameter or the functional form sign. So this is the bias, and expected value of T theta x minus of sin theta. That means the differences between the estimated value for the theta and the actual value and we have considered the average of those values, then this is called the bias. Also, this bias have either greater than 0 or less than 0 or equal to 0. Since if it is a greater than 0, it is a positive bias, less than 0, negative bias, and if equal to 0, it is actually unbiased. Na? So when an estimator is an positive have positive bias, then it overestimates the parameter. Then it's overestimate. Okay, that means the actual value is 7. Then it estimate the value more than 7 actually. Okay, and for negative bias, it is underestimate. And for the case of unbiased, there is no estimate. That are symmetrical in nature. So yes. Now we have, since we have discussed about unbiased statistics, we have locally minimum variance unbiased estimator. Like that is locally minimum variance unbiased estimator. Okay, that is LMVUE. Okay, so suppose we have a theta naught, which is belongs to the parameter space capital theta. So like let we have a theta naught parameter which belongs to the capital theta, that is the parameter space, and suppose sorry and suppose u theta naught be the class of all unbiased estimator, be the class of all unbiased estimator. Suppose that class will be u theta naught, and that the unbiased estimator are like tx of the parameter theta naught. Okay, such that like the expected value of t square is finite. That means it exists actually. The expected value of t square exists. Okay. Then suppose t naught, which is also belong to the same class of unbiased estimator, u theta naught. This is called locally minimum variance unbiased estimator of theta if the expected value of under theta naught, obviously expected value of t naught minus theta naught whole square is less than or equal to expected value of cos theta naught, it is t minus theta naught whole square for all t belongs to the unbiased estimate class u theta naught. So that means what? We have more than one unbiased estimator for the same parameter. Okay, but those which have the minimum expected value of t naught minus theta naught whole square is the locally minimum variance unbiased estimator. Okay, in a similar manner, like we have a global, or sorry, not global, that means uniformly, obviously. Okay, we also have like uniform minimum variance unbiased estimator. Okay, so that is UMVUE. Okay, this has the same definition, but since locally minimum variance and unbiased estimator is like the estimator has minimum variance for a particular value of the parameter, say theta naught, that as we have discussed here, we have taken a particular value of theta as theta naught. Okay, and then this contain the minimum variance, and it is an unbiased. So it is unbiased estimator and having a minimum variance for the particular value of the parameter theta naught. So it is called locally minimum variance unbiased estimator. But when we are discussing about the uniformly minimum variance unbiased estimator, then it can take the minimum variance for all values of the theta, not for the particular value of the theta, but we can take the all values or any values within the range of the theta. Okay, so here the definition will be like, let u theta be the class of all unbiased estimator, and tx is the unbiased estimator, obviously, such that the expected value of t is finite. Okay, for all theta belongs to the parameter space capital theta, then t naught, which is belongs to the class of all unbiased estimator, is said to be uniformly minimum variance unbiased estimator if expected value of t naught minus theta whole square is less than or equal to expected value of t minus theta whole square for all theta belongs to the capital theta. Okay, and the same definition we have written above, but for a particular value of theta, and we have considered that particular value as theta naught. So this is called the uniformly minimum variance unbiased estimator. That means in the class of unbiased estimator, uh, estimator that have the minimum variance is called the uniformly minimum variance unbiased estimator. Okay, and now we can estimate, or we can calculate, or we can find out the uniformly minimum variance unbiased estimator with the help of one of the famous inequality, that is Kramer-Rao inequality. Okay, so it is like Kramer and Rao, Kramer-Rao inequality, or in short, we are usually call it CR inequality. Okay, so suppose we have a family. Let me write the statement, or let me say the statement and write the mathematical form only. Suppose suppose we have a family of distribution, like it is f, x, and the parameter theta, such that theta belongs to the capital theta, which is parameter space. This satisfies the following regularity condition. So there are some regularity conditions that this family must follow. And those regularity conditions are like the set. Suppose the set we have S, a set where this member of a family fx theta is non-zero, is non-zero, uh, and is independent of theta. Okay, this S, that is support set. Okay, the range in which the theta may vary. Okay, the possible values of the theta, that means this is called support set. So this must be non-zero and is independent of theta. Okay, the second is for x belong to this support set capital S, and for the parameter theta belongs to the parameter space capital theta, the derivative like del of del theta f of x theta exist and is finite. Exist and finite. Uh, when like we are dealing with the single parameter, then that partial derivative will be replaced by the total derivative, that is d d theta of fx theta. But in case when we have more than one parameter, then instead of the total derivative, or we will use the partial derivative. Okay, so these exist and is finite. And for any statistic Sx with expected value of Sx is finite for all theta, the following holds. The following condition holds. Okay, like d d theta of integral over of S x f x theta. This is equal to like integral over of Sx d d theta of like fx theta dx. Okay, if this three condition holds, okay, then like the variance of the estimator, which is used to estimate the parameter, is always greater than or equal to psi dash of theta whole square divided by I theta. Here I theta is nothing but the Fisher information matrix. Okay, here like I theta is defined as like the expected value of del theta of log of PDF fx theta whole square. Okay, this, and also we know that this I theta must be finite as well, so that we can calculate the variability, okay, of that estimator Tx. Okay, so this gives the when it is like when the equality condition holds. Suppose we have one. Okay, let me write. Suppose we have T1x, we have T2x, we have similarly Tnx. Okay, we have different unbiased estimator. Okay, and in these n by unbiased estimator, one estimator has a variance which is equal to this star. Okay, and the other is greater than or may possible that also equal to. But when an estimator which have the same variance as given in star, equality condition holds for the very given in star, okay, then that estimator is uniformly minimum variance unbiased estimator for the parameter or the function of the parameter. Okay, so this is how like we are use CR inequality to find the uniformly minimum variance unbiased estimator in the class of unbiased estimator. Okay, we have one remark actually. Let me write here only. Like if variance of Tx attains the lower bound, then Tx is the, that is already I have mentioned, but let me write. If variance of Tx attains the lower bound, then the Tx is nothing but the uniformly minimum variance unbiased estimate for psi theta. Okay. Uh, Now we have discussed about the unbiasedness, the locally minimum variance unbiased estimate, the uniformly minimum variance unbiased estimate, and then how to calculate the uniformly minimum variance unbiased estimate with the help of the Kramer-Rao inequality. Now the next topic is relative efficiency. So that is relative efficient estimator. Okay. Okay. relative efficient estimator. So suppose we have like T1x, we have one estimator which is T1x, the other estimator is T2x, and the both are like unbiased. Both are unbiased estimator of theta. Okay. Now that means what? That means the expected value of T1x is equal to 0, not 0, it is theta, which is also equal to the expected value of T2x. Now, we need to find which is relatively efficient. Okay, which estimator is relatively efficient than the other estimator. That means which is better. Better means that have the minimum variance. Okay, so the first one is like the relative efficiency. Okay, is like defined as the variance of suppose T1x and variance of T2x. Just a simple logic here. Okay, so it is possible that it is either greater than 0 or equal less than 0 or equal to. Let me write it one only. Okay, so if variance of this RE, the value of RE is greater than 1, that implies the variance of T1x is greater than that of the variance is T2x. That means here like T2 is efficient. Okay, and similarly, the value is less than 1. This implies the numerator value is smaller than the denominator one. That means the variance of the T1x is less. This means T1 is efficient. Okay, and once we have the both the estimator, then we are like both are equally efficient, like equally efficient. Uh, okay, so like we have an example for this actually. Like if you people know about like maybe you people remember about the Poisson distribution. Like let a random variable x follows Poisson distribution with the parameter lambda, where lambda is unknown. Okay, so in that case, we know that the expected value of x, the mean value, that means uh, is lambda, and the variance of x is also lambda. That this is all we have already discussed in the fourth week, actually, if you may remember. Okay, and since we know that, like the sample mean, and sample variance, sample variance, both are like small s square, are unbiased estimate. Both are unbiased estimator, uh, like for the parameter lambda. Okay, but when we like calculate the variance of this, then we will find out the variance of x bar is less than and maybe sometime equal to variance of s square. So this implies the variance of the x bar estimator is less as compared to the variance of s square. So this implies what? X bar is like relatively efficient than s square, that is sample variance. Okay, so we have more than one variance, sorry, more than one estimators, but on the among those estimators, having the estimator having the minimum variance is like the relatively efficient estimator. Okay, now we have one more definition, that is efficient estimator. That means we have discussed about the unbiasedness. Now we will discuss about the efficient estimator. Okay, so suppose we have a let T1x be an unbiased estimator. Okay, so T1x be an unbiased estimator. Okay, of psi theta. then the Tx is said to be an efficient estimator of of sine theta for all theta belongs to capital theta if the variance achieve the equality in the CRLB, that means Kramer-Rao lower bound. That means the variance of Tx is equal to like psi dash of theta whole square divided by I theta. If this condition holds, then we say that this is nothing but the Kramer or lower bound actually, CRLB. This is called, okay, this is called Kramer or lower bound. Then this Tx is called the most efficient or efficient estimator. Okay, then like this is called the efficient estimator. Then Tx is efficient estimator. Okay, we have one remark related to this as well. Like an efficient estimator is always an unbiased estimator, but the converse need not be true. An efficient estimator is always an unbiased estimator. The converse need not be true. Okay. Uh, Now we will discuss about the third, that is consistent estimator. Okay. So, sup sorry. So suppose we have a TNX, that is a sequence of estimators based on the sample values of, okay, let me write, it is a definitions for this. Like let we have a TNX for n equal to 1, 2, and so on. Be a sequence of estimator. Sequence of estimator. Okay, based on the samples. Based on the samples like x1, x2, xn of parameter theta. Okay, then we say that like TNX, we say that TNX is a consistent estimator. This is a consistent estimator of the parameter theta if for every epsilon is greater than 0, limit n tends to infinity, the probability that the estimate value minus the true value, the difference between the estimate value and the true value is greater than epsilon, the probability lies to, converges to 0. Okay, then we say that this Tn is an more consistent estimator. Okay, but since this probability is not possible, like not easy to compute, so using Chebyshev's inequality, we will simplify this and we will give a necessary and sufficient condition to check whether the given estimate is a consistent estimator or not. Okay, so like The alternative definition we can say, okay, suppose we can say that the t is consistent if limit n tends to infinity, the expected value of t and x equal to theta. This implies kind of it converges to theta. That means uh, unbiasedness condition may hold for the large value of n, and limit n tends to infinity, the variance of this estimator equals 0. So if for the large value of n, the expected value gives the parameter value and the variance gives it 0, then it is said to be a consistent estimator. Okay. Now the next one is sufficient estimator. Okay. Sufficient statistics or sufficient estimator is like mainly used to reduce the dimension. Okay. It is mainly used to reduce the dimension of the data or the estimator. Okay, like we have x1, x2, and xn samples. Okay, we have n dimensional data. Okay, and suppose we have one functional form of these n dimensional sample which contains the same amount of information that contains in the whole sample. Okay, suppose x1, x2, and xn have the amount of information which is same as for some functional form of the so these random samples, then both are like similar in nature. But if we are able to reduce the dimensionality of this with the help of the functional form, then we say that that functional form or the statistics is called the sufficient statistics or sufficient estimator. Okay, this is just for the understanding purpose only actually. Standard definition is like this, like let x, that is a sample of x1, x2, and xn. It is a random sample from distribution having the capital fx cdf. Okay, and then a statistics t, then a statistics, suppose we have a statistics t, it is said to be is sufficient, is sufficient for the parameter theta or the family of the distribution from where this samples is taken from. Okay, if and only if the conditional distribution of x given t does not depend on theta. If and only if, like, the conditional distribution of x given t does not depend on the parameter theta. That means the conditional distribution of the sample given the estimator is independent of the parameter. Then we say that that estimator is a sufficient statistics or sufficient estimator. Also, like it can be seen that shown that the statistics is sufficient for the family of distribution if we have 3 points and one, at least one may hold. Okay, so that already discussed in the class. I'm not like writing, it may take time actually. Okay, so this is how we may use. like one example is discussed in the lectures actually. Suppose we have a random sample of one example is discussed. Suppose like x1, x2, xn are samples from the Bernoulli distribution. Bernoulli distribution. Then if you are like using the formula, using the definition actually, then we may find the summation of xi like is sufficient for the parameter p. Okay, the Bernoulli parameter, this probability of success, this is the sufficient statistics is actually summation xi. Okay, we will solve some numericals based on these actually. Okay, So these are the four properties of a good estimator. Okay, now we are like we will discuss about the estimation methods or method of estimation. Okay, the first one is, am I audible now? Can anyone confirm? Am I audible?
Yes, sir.
Okay, okay. Now we will discuss about the estimation methods, and the first method is method of moments. Okay, so like in this method, we simply we simply equate sample moments with their population counterpart, with their population counterparts, and then solve for the parameter. Okay, so this is like how we need to estimate. Okay, so this is how like method of moments works. Suppose, for example, we will use mu r dash, which is defined as the expected value of x to the power r. These are the rth order population moment. Okay, and also mr dash, which is 1 by n summation xi to the power r. These are suppose rth order sample moment. Okay, so we have sample moment, we have population moment, and then we will like equate these two and solve for the parameter. Then the that value that we have estimated is nothing but the method of moment estimator. Oh, sorry, that is the method of moments. Okay, or moment estimator. Okay, let's discuss it with some example. We are given a probability density function which is equal to 2x theta square for x lie within 0 to 1 by theta square. Okay. We need to find the method of we with the help of the method of moment, we need to find the estimate for the parameter theta. Okay, using the method of moments. Okay, so obviously the first is like population parameter. Since we have one parameter here, so the first order population moment is like is used to calculate this value. But in case if first order moment is not available or some other reasons, then we will use the higher order moments to calculate the parameter or estimate the parameter. Okay, so the population moment mu r dash, which is expected value of xr. Okay, here since there is only one parameter, so we have considered r equal to 1. So mu1 dash, which is expected value of x, which is defined as like 0 to 1 upon theta square x into 2x theta square dx. Okay, so like 2 theta square comes out common, 0 to 1 upon theta square, x square dx is there. So 2 theta square x cube by 3, 0 to 1 upon theta square. So just 2 theta square, like 1 by theta to the power 6 is there, and then 0 is there, theta square. Then after solving, I'm just writing the final 2 upon 3 theta. Okay, just after solving, we will get 2 upon 3 theta. Actually, here I am taking one mistake. Here only theta is there, not theta square actually. Okay. So when we are calculating, we will find out like 1 by 3 theta cube minus 0 and theta square theta. So 2 by 3 is there and theta. So this is the expected value. So the population parameter is 2 by 3 theta. Now, uh, we can eh, we can use this and we can also like solve the second order and we will find out after solution like 2 theta square. Okay, if you are like able to solve, I don't think it is needed, but still since it is written, so I have written there. Okay, now since okay, so these are already discussed in the actually, so I'm just writing theta square cap which is 2 by n summation over xi square and inverse. Then this is the like moment estimator for the theta square. Okay, we need to calculate the moment estimator for the theta square only actually. That's why we have one more remark actually. The method of moment is the oldest method of deriving the point estimator. Okay, the method of moment is the oldest method of deriving the point estimates. It is almost like produce asymptotically unbiased estimator, not unbiased, but approximately asymptotically unbiased estimator is produced with the help of the method of moment estimator. Yes, and yes, in some cases, the method of moment estimator does not exist. So in that case, we use the method of maximum likelihood estimation or maximum likelihood estimation or estimators. Okay, MLEs. In short, we will call it MLEs. Okay, so in MLEs, suppose like we have X1, X2, Xn are random samples taken from a population. Suppose like fx theta is the population or the PDF of the population. From there, we have taken the random sample X1, X2 up to Xn of size n. Then, in maximum likelihood estimation, our aim is to first construct the likelihood function L. Okay, a likelihood function is constructed with the help of the given the known functional form. This is product of I from 1 to n. The okay, so it is defined as the product of the probability density function. Where theta belong to the parameter space capital theta. Okay, so the first step is to construct the likelihood function. Okay, then we will find the value of theta for which this likelihood function is maximized, gives the maximum value. That means, okay, so that is called the maximum likelihood estimate. Okay, and yes, let me give one example actually so that it is more clear. Okay, suppose we have a random sample like x1, x2, xn, the random sample from okay, we can take exponential lambda. Okay, find the maximum likelihood estimate of the parameter lambda. Okay. So, okay, let's start. So we know that since x follows the exponential distribution, then the PDF form is lambda e to the power minus lambda x for x is greater than 0, lambda is greater than 0. Okay. Now our aim is to first construct the likelihood function. So likelihood function L, which is lambda x, is defined as like product of I from 1 to n this. Okay. Now lambda e to the power minus lambda xi. Okay. So lambda is taken as common. So lambda to the power n is there, e to the power minus lambda. And this is summation of xi actually. Okay. If you may see I from 1 to n summation of xi. Okay. Now we can scale down with the help of the taking log in both sides. Okay. Because like it still attains the same value, the maximum value attains at the same point for the parameter lambda. Okay, so it just scale down the function and nothing, and it like it is more comfortable or easy to deal with the log function, a log likelihood function as compared to log function, sorry, at compared to the likelihood function only. Okay, so either you may take this function, but then it is quite tedious to calculate the maximum likelihood estimate. So we have considered the log likelihood function. Okay, so taking log in both sides. So if taking the log, then it is like n log lambda minus lambda times of summation of xi from 1 to n. So it is like quite simple. Now, this is the log likelihood function. This suppose equation 1 is a log likelihood function. Now, the second step is to find the value of the parameter lambda for which this log likelihood function is maximized. Okay, so that means we can use the logic of calculus, the concept of calculus, where we first differentiate this with respect to lambda. So TD lambda of ln of, okay, so it is n by lambda, okay, minus it is summation of xi. Okay, and then we equate this log like the differentiation or the derivative of the log likelihood function to 0. This equation 2 is called the likelihood equation actually. Okay, when we differentiate the log likelihood function with respect to the parameter and then equate those expression to 0, then that equation is called the log likelihood equation. Okay, now to solve this equation, since we have only one parameter, so we can solve this, and once like n by lambda equal to summation of xi, then lambda cap equal to n upon summation of xi 1 upon like x bar. Okay, so this is the uh, this lambda is actually the parameter, but lambda cap is the maximum likelihood estimator of the parameter lambda. Okay, so this is 1 by x bar. Okay, it is the reciprocal of the sample mean. So then we say that the maximum likelihood estimate for the parameter lambda is 1 by x bar. Okay, that means what? That means at lambda equal to 1 by x bar, this the above log function, log likelihood function of lambda has maximum. So that it is a maximum likelihood estimate. Okay. uh, we can also solve different questions that we will solve. Now the next topic is interval estimation. Okay, So up to this point, we have considered we have discussed about the method of estimation, in which we discussed method of moment estimator and maximum likelihood estimation. There are more methods to estimate the parameters, like least square method, uniformly minimum variance estimator, chi-square methods is there, and then maximum product spacing method is there. Okay, so lot of approach is there to estimate the parameter. But since it is an introductory course, we have covered only the method of moment estimator and the maximum likelihood estimator, because these two are used maximum of the time. Okay. And just like maximum likelihood estimator is always consistent in nature. So that's why we may use different kinds of distribution estimation methods or estimators. Okay. Now the interval estimators. So okay, let me write. Suppose is x bar is the mean of the sample of size 1. Like if x bar is the sample mean of size n. Okay. Okay. That means it is a sample mean, and the mean has the sample has contained n observation, and from normally distribution, normally distributed normally distributed population with known variance. Okay. Uh, with known variance sigma square and a known mean mu. Okay, so the mean is unknown, but the variance is known. Then in that case, then 1 minus alpha 100% confidence interval for the population mean is given by like this, like x bar minus z alpha by 2 sigma by root 10 mu x bar plus z alpha by 2 sigma by root 10. So this mu lie within the x bar plus minus z alpha by 2 times of sigma by root 10. Okay, where like z is the where z alpha by 2 is the actually upper quantile. Okay, and is defined as probability that z is greater than z alpha by 2 is having probability alpha by 2. Okay, so this value is taken from the normal table only. Okay, so this is how we construct the interval estimate or the confidence interval at alpha level of significance when the variance is known, the sigma square is known. Okay, so like in case population variance is unknown. Okay, but in that case, since population variance is also unknown, then we use the estimate of the population variance. Okay, the estimate of the population variance, that is the sample variance. Okay, so we use the sample variance to construct the confidence interval for the mean, population mean mu. Okay, so like the case is when population variance is unknown, then in that case only uh, we use the student's t distribution. Okay, we replace the normal distribution with the student t distribution, and the value in place of the population variance we use the sample variance. Okay, so in that case the interval becomes like x bar minus t n minus 1 degree of freedom that we have already discussed in the previous week lecture. Okay, s upon root n. Okay, mu x bar plus t n minus 1 alpha by 2 s upon root n. So this is the confidence interval when the variance is unknown. Okay. Here again, like the probability that t is greater than t n minus 1 alpha by 2 is alpha by 2. Similar. Okay. So we have questions let's do it one question. Like for example, suppose the average return of a risky portfolio is 10.5%. Okay. We are given the average return of a risky portfolio is 10.5%. Okay. Per year with a standard deviation, which is like sigma is given here at 18% per year. Okay. If if returns are assumed to be normal distribution, so we need to construct a 95% confidence interval for the portfolio return next year. Okay. So like we need to construct a 95% confidence interval. Okay. We need to construct 95% confidence interval uh, for the like return. Let's say R. Okay. So here mu is given. We know that mu. Okay, so these are already given. Okay, actually not mu here. We need to write x bar. Na? Okay, so this is how the confidence interval is calculated. Minus is for lower limit and plus is for upper limit. And also z 0.0, sorry, 0.05 by 2. The value of this is nothing but 1.96. At 95% confidence interval, the value of z is 1.96. Okay, these are already well known actually. So the class interval, sorry, not class interval, the confidence interval. So the confidence interval is 10.5 plus minus 1.96 into 18. Okay, so 10.5 plus minus this will be like 35.28. And once you are like able to solve, you will find the confidence interval. The minimum value is minus of 24.78 and the maximum value is 45.78. Okay, so this is the confidence interval. This is the 95% confidence interval. That means the true value of the portfolio return for the next year is lie within minus 24.78% to 45.78%. That the probability of this is 95%. Okay, so this is the 95% confidence interval. Similarly, like we have one more question. Okay, similar question is there. Okay, like suppose consider a queuing system which describes the number of outgoing telephone calls in a particular telephone exchange. Okay, so determine 95% confidence interval for the average talk time in seconds of the customer in the system if a random selection of 15 customers yield the following data. Actually, we are given a data. Okay, I am writing the data 54, 53, 58, 72, 49, 92, 70, 71, 104, 48, 65, 72, again 65, 70, and the last one is 85. These data are given only. Okay, and then uh, that means we need to like construct the uh, confidence interval, 95% confidence interval for the average, for the mean. Okay, and we are given the data only. So with the help of the data we are able to calculate x bar. Okay, we are able to calculate x bar, uh, that is 1 by n summation of xi. Okay, you may solve and you will find 68.53 after solution. Okay. Am I audible na, to all of you? Is there anyone who can confirm I'm audible or not?
Yes, sir.
Okay. Uh, okay, so x bar can be calculated with the help of these given data. Okay, and then again here still we don't have known some population variance. So instead of since we do not have population variance, we can use the sample variance. Okay, so the sample variance s square is like 1 upon n minus 1 summation of xi minus x bar whole square. We have already calculated this. Okay, we are not like performing the simple calculation only. Okay, so it is comes out to be 250.2724, and then the standard deviation or the s is here, it's 15.82. Okay, now since the population variance is unknown, then in that case we use t distribution instead of normal distribution. Okay, that we have already discussed in the previous slide. So we are given n equal to 15. So the t value at 15 minus 1, that is 14 degree of freedom, at 595, that means 0.00, sorry, 0.025. This value from the t table obviously comes out to be 2.145. Okay, now our aim is to calculate the or construct the confidence interval. So the confidence interval will be like again 68.53, that is the x bar, plus minus like it is the t at 14, 0.025. Okay, let me write the formula first. X bar minus plus t at 14, 0.025. Okay, and then s by root n. Okay, this is the formula. So obviously x bar is 68.53. Okay, it's minus plus, it's 2.145 multiplied by the value of s is 15.82 and under root 50. Okay, so just simple calculation again, like we need to solve this. So it's 68.53 minus plus the numerator value comes out to be 33.9339 and divided by 3.8730. These are the approximate value for the root 15. Okay, so obviously 68.53, it's minus plus. These fraction gives actually 8.7617. Okay, so when we consider the minus sign, so it will give 68.53 minus 8.7617, and after solution we will get 59.7683, and when we add these two quantities, it will give 77.2917. So the 95% confidence interval is 59 point this to 77.29 something. Okay. So this is how we are able to solve the numericals related to the confidence interval. We also have difference between the means of two populations. Uh, Before this, we are discussing about the single mean actually. Here, what if we have a difference of means? Okay, like difference between the means of two population, then how we can construct the confidence interval in that scenario? Difference between the means of two population. Okay, so like suppose x1 bar follows normal with mean mu1 and the variance sigma is square 1 by n1. Okay, similarly x2 bar follows normal with mean mu2, the variance sigma 2 square by n2, and these are like independent in nature. So x1 bar minus x2 bar again follows normal distribution with mean mu1 minus mu2, and the variability is like sigma 1 square upon n1 plus sigma 2 square upon n2. Okay, these are the simple properties of normal distribution, which we have discussed in week 4 actually. Okay, now the difference is this. So how to calculate the confidence interval for the difference between the means mu1 and mu2? Okay, so okay, so the confidence interval for mu1 minus mu2 at like 95% or not any confidence interval actually at like let me write first currently alpha level of significance. Okay, so this is actually like x1 bar minus x2 bar minus plus z alpha by 2 and sigma 1 square upon n1 plus sigma 2 square upon n2. So this is how we calculate the we construct the confidence interval uh, for the difference between the means of two population. Okay. Again, we have one more scenario like if population variance are unknown, then in that case, instead of the population variance, we use the pooled variance. Okay, we use the pooled variance. Uh, okay, let me write. If sigma I square is unknown, then in that case, we define a quantity SP, which is actually n1 minus 1 S1 square plus n2 minus 1 S2 square upon n1 plus n2 minus 2. Okay, so this is the quantity. This is nothing but the weighted mean of the individual sample variance, and this is called the pooled variance. This is called actually pooled variance. Okay, then the confidence interval for mu1 minus mu2 is again x1 bar minus x2 bar minus plus is there. Now T alpha by 2 n1 plus n2 minus 2 sp, the pool variance. Okay, 1 upon n1 plus 1 upon n2. So this is how we calculate, we construct the confidence interval uh, when we don't have the population variance. Okay. Now we have a question actually. It is a like nice question. Like in sampling from a non-normal distribution, okay, uh, with variance of 25. Okay, so we are given variance that is sigma square is 25. How large must the sample size be? The question is how large must the sample size be so that the length of a 95% confidence interval, the length of a 95% confidence interval for the mean is 1.96. Okay, so we need to find the sample size n for which for the 95% confidence interval have interval length 1.96. Okay, okay, so we are given the confidence interval when sample is taken from the non okay, let me write first. Okay, so we know that this is x bar, this is minus plus z alpha by 2 is there and sigma by root n. These are already given. Okay, thus we are given the length of Ci. How can we calculate the length? Okay, since we know that in x bar term, this z alpha by 2 sigma by root n is subtracted and in added as well. Okay, so obviously the length, the interval length is suppose small l is there twice of z alpha by 2 sigma by root n. This is the interval length only. Okay, so we can write 2 into we are discussing 95%, so obviously it again 1.96. Please don't be confused. 95% and 1.96 coincidentally both are equal actually. Okay, into the sigma square is given as 25, so the value of sigma is 5 and root n. The value of n is here actually don't know. We need to calculate the n actually. Okay, now we are given in the question the length is also 1.96. Okay, don't be confused with this like z alpha by 2 and l. Okay, since the small l is also given as 1.96. Okay, so we can write 1.96 equal to 2 into 1.96 into 5 divided by root n. Okay, so 1.596 is cancelled out. Okay, so that means what? Like root n equal to 10. So this implies n equal to 100. Simple. So the sample size, thus the sample size should be thus the sample size should be 100 so that the length of 95% confidence interval will be 1.96. Okay, so the length will be 1.96 and the 95% confidence, the Z value at the 95% confidence interval or 5% level of significance is 1.96. So both are like coincidentally similar. Okay, so this is how we calculate. Now the next question is like confidence interval for population variance. Up to this point, we have constructed the confidence interval for sample population mean and the difference of mean. Now the confidence interval for population variance is like, suppose we are given S square, that is the sample variance. Okay, having from a sample of size n, and we need to construct the 1 minus alpha 100% of uh, confidence interval for the variance. So the formula for this is like n minus 1 s square upon like chi square alpha by 2 n minus 1 sigma square n minus 1 s square chi square 1 minus alpha by 2 n minus 1. Here, since t distribution and z distribution or the normal distribution are symmetrical in nature, so we have considered alpha by 2 in both sides. Okay, like here you can see the z alpha by 2 is there in the solution, uh, in the above SO for the t as well. But here chi-square distribution is not like symmetrical in nature. It is positively in nature, positively skewed actually. Okay, so that means we have like different shapes. Like if so, that means here it is one value and here it is another value. So at one value it is like chi square 1 minus alpha by 2, and at so other point it is alpha by 2. Okay, so these are the topics like we have covered. We have solved some numericals as well. Let's solve some more numericals. Okay. If anyone have any doubt, they can ask, or we can solve some more numericals based on the topics we have covered today. Like suppose let x1, x2, xn be IID random variable with PDF. We are given the PDF fx theta, which is equal to theta x to the power theta minus 1. The value of x lie within 0 to 1, and theta is strictly greater than 0. We need to calculate, find MLE of theta. Okay, we need to calculate the or estimate the MLE of theta. Now we are given the PDF. We need to find the MLE. So our first step is to construct the likelihood function. So the likelihood function is like product of I from 1 to n f of xi theta. So product I from 1 to n theta x to the power theta minus 1 is there. Okay, so theta to the power n, and then product of xi to the power theta minus 1. Okay, so this is the likelihood function. Now we have taken log likelihood for the simplification purpose only. Okay, so consider log ln of L. So taking log n log theta plus theta minus 1. Okay, and when we consider log of product of xi equal to summation of log of xi, that we all already know, summation of log of xi I from 1 to n here. Okay, so this is the log likelihood function. Okay, this is the log likelihood function. Now since there is only one parameter, our aim is to differentiate this log likelihood function with respect to theta only. Okay, so d theta of log L, it is like n by theta is here. Okay, and here it is like plus summation I from 1 to n log of xi. Okay, this is the log likelihood equation, and we need to equate this equation to 0, and then with the help of this equation we solve this for x, for theta only. Okay, for theta. So obviously it is like minus times of like summation log of xi. So from here only theta cap is the MLE of theta. MLE of the parameter theta is n upon minus is there summation ln of xi. So it is minus times of n upon summation of log of xi. So this is the maximum likelihood estimate for the parameter theta when the random variable x follows the distribution which is given theta x to the power theta minus 1 within the range 0 to 1. Okay, so this is how we calculate the maximum likelihood estimate. Okay, like we can even also calculate the method of moment estimator for the theta. Okay, let for the same question, like for the above question, like find the method of moment estimator for the parameter theta. Okay, so like we are given the PDF is like theta x to the power theta minus 1. Okay, theta x to the power theta minus 1 for x lie within 0 to 1, theta is greater than 0. Okay, now for the likelihood, we have constructed the likelihood function, then log likelihood function, then differentiate that log likelihood function with respect to the parameter, and then equate it to 0 and solve for the parameter theta. We have the log likelihood, sorry, estimate, ML, maximum likelihood estimate. But for the moment estimator, we need like population moment and sample moment. Okay, so like for the population moment, we have like expected value of x, which is what? Integral over 0 to 1 x into fx dx. Okay, simple. It is 0 to 1 x into theta x to the power theta minus 1 dx. Theta is taken out common. It's x to the power theta dx. So this implies what? Expected value of x is theta x to the power theta plus 1 upon theta plus 1. 0 to 1 is there. So we have considering 1, then expected value of x is like theta upon theta plus 1. Okay, so we have the population moment. Now the sample moment m1 is like 1 by n summation of xi, which is nothing but x bar actually. Okay, we can use m1 or x bar or whatever we want. Okay, like summation of xi, which is x bar. Okay, so now we need to equate these two. So theta upon, okay, let me write in a manner. So it expected value of x equal to x bar. The population moment is equated with the sample moment. Okay, so that is theta upon theta plus 1 is x bar here. Now we need to solve for the theta actually. Here it is solved for the x bar only. So we need to solve for the theta. So theta equal to like x bar theta plus x bar. Okay, so theta minus x bar theta equal to x bar. Now taking theta as common, 1 minus x bar equal to x bar. Now the theta cap is used for the estimate. Okay, theta cap, that is the method of moment estimator here. It is the method of moment estimator. It is x bar upon 1 minus x bar. Okay, So this is the method of moment estimator or the moment estimator for the parameter theta. Now, uh, now the MLE comes out to be like minus times of n of summation log base e, obviously natural log is there, xi. So this is the maximum likelihood estimate for the parameter, and this is the method of moment estimator for the parameter. These two method gives the estimate for the parameter actually. Okay, but have two different nature. Okay, and like we can solve the variance of these parameters. Okay, this theta cap and the method of moment estimator, and this we can check the efficiency, which perform better, which perform like which is like better estimate for the parameter theta. So these can be like calculated here. Okay. Uh, now we have one more questions. Like let x1, x2, xn be a random sample from geometric distribution with parameter theta. Okay, where theta is unknown. Okay, based on this random sample, based on this random sample, find the maximum likelihood estimators. Find the MLE, maximum likelihood estimator of the parameter theta. Okay, so okay, let's solve this question as well with the similar approach. Actually, previously we have solved for the continuous kind of random variable, that is theta x to the power theta minus 1. But here it is a discrete random variable, but the approach is same. Okay, but the approach is same. So let's start. Here given we are given like x follows geometric theta distribution. Okay, so that means what? The probability distribution function x is like 1 minus theta to the power x minus 1 into theta. This is the probability mass function for the geometric random variable. Okay. Now we have the probability mass function. The next step is to construct the likelihood function. Now the likelihood function, that is L. Okay. It is like product of those. So these are independent. So like it is like x1 of x1 into like probability mass function of x2 random variable. Okay, and probability mass function of xn random variable, because we have considered n random samples. Okay, now again putting those values. So it is 1 minus theta. 1 minus theta is repeated n times. Okay, and theta is repeated n times. So 1 minus theta to the power 1 minus x. So that means 1 minus theta to the x minus 1. Sorry. 1 minus theta to the power x minus 1 and theta to the power, uh, theta to power 1 actually. So 1 minus theta is repeated n number of times. The 1 minus theta to the power x minus 1 is repeated n number of times. So this gives actually 1 minus theta summation of xi minus n. And theta is repeated n number of times. So it is theta to the power n. So the likelihood function is like this. Let me write it in equation 1. Okay, now for the simplicity purpose, again taking log both side. So it is log of L. Okay, log likelihood function. So when we consider log, then it is summation of xi minus n log of 1 minus theta plus n log of theta. Okay, summation xi minus n log of 1 minus theta plus n log of theta. So this is our equation 2, which is the log likelihood function. Now our aim is to differentiate this log likelihood function with respect to the parameter theta. So that means d d theta of log L is when we differentiate it with respect to the parameter theta, it is like the first is constant, summation xi by n is there. Then log of 1 minus theta is 1 upon 1 minus theta. Then 1 minus theta, that is minus theta. So it comes out to be minus 1. Okay. So it is minus 1 upon 1 minus theta is there. Plus n log theta is n by theta only. And then equate this log likelihood equation to 0. This is equation 3. So equation 3 is the log likelihood equation. And then with the help of this equation 3, we can solve for the theta. Okay. So from here, n by theta is summation x by n 1 minus theta. Okay, now it's like simple. Okay, we need to solve for the theta only. Okay, we need to just transform those. Okay, and transform, and at last after transformation, we will find. I'm just writing the solution. Okay, theta cap of MLE, that is the maximum likelihood estimator. That is n upon summation of xi. We have considered I from 1 to n. Okay, so this is the maximum likelihood estimate for the parameter theta when theta is the geometric parameter. Okay, it is a parameter of from the geometric distribution. Okay, so this is how we can calculate the maximum likelihood estimators under the discrete random variable, for the discrete random variable even. Okay, now the next question is okay, suppose we are given a sample of 100 measurements, a sample of 100 measurements at breaking strength of cotton thread, strength of cotton thread gave a mean of 7.4 and a standard deviation of 1.2 gram 1.2 grams. Okay, now construct 95% confidence interval, 95% confidence interval for the mean breaking strength of cotton thread. For the mean breaking strength of cotton thread. Okay, so we need to construct the construct the confidence interval for the mean. Okay, so that means, and we are given the standard deviation. Okay, we are given the standard deviation, the sample is given, not the variance is given. Okay, and here the sample size is also given. So let's solve this. If you read the question, you will find out the sample size is 100, which is quite large. In statistics, like 30 or more than 30 is a large number. We have considered large number if the values are 30 or more than 30. It is like quite large. Okay, in comparison to 30, it is quite large. So in that case, like x, we are also like given x bar equal to, let me write again, 7.4 gram. Okay, it is given. Since like we are not given the sigma actually, we are not given the sigma, we are given the s. Okay, sigma is unknown. Okay, sigma is unknown, but like the s is 1.2, it is known. So in this problem, since n is quite large, then if n is quite large, the sigma value is like similar to the s value. Okay, or the z table, if you are using the same formula, then the z table and the t table have the similar value when n is quite large. Okay, here n is 100, so we directly use the z. Okay, and then z alpha by 2 at 95% confidence interval 1.96. Okay, so these are like this. Now the 95% confidence interval for mu is like x bar minus plus z alpha. Okay, here sigma by root 10. Okay, so this formula is directly used because sigma is, instead of sigma we use sigma cap, or we can use x bar minus plus like t. Okay, that we have used na, like t distribution is there. So just wait. It's n minus 1 degree of freedom at alpha by 2 and it's s by root 10. Okay, since n is large na, then z alpha by 2 is equal to like t n minus 1 alpha by 2 for large n actually. Okay, we have the same table, so that's why we use the direct any one of the formula. Okay, so just putting the values, nothing else, like 7.4, it's minus plus, it's 1.96. Also one more thing, here s is 1.2, so it's 1.2 divided by root n. Root n means like under root of 100. Okay, so this is like 7.4 minus plus 1.96 into 1.2 divided by 10 is there. Okay, so it is like 7.4, it's minus plus after solution to 2352 actually, it's 2352 is this. So when 7.4 minus 0.2352, it comes out to be 7.1650, we may say. Okay, and then if we add, then it is like 7.6352. Okay, if you want, you can write for it here, or then that means what? That means 7.1648 mu 7.6352. So this is the 95% confidence interval. So this implies what? This implies that the probability that the true value of the population mean breaking strength of the cotton thread will fall in the interval 7.1648 to 7.6352 at 95% level, at 95% confidence level. So this is the meaning of this answer. Okay. So these are the questions. Like we have one more question actually. I have two questions. Quick question, and then we will conclude our session. Like here we are given like fx is, we are given 1 by theta. Okay, and 0 x lie between 0 to theta. This is nothing but the uniform distribution actually. Okay, this is the uniform distribution. We need to find the method of moment estimator for the theta. Find the method of moment estimator for the theta. Since we know that it is a uniform distribution, so in that case, expected value of x is like theta by 2, b plus a by 2. So theta plus 0 by 2. So theta by 2 is there. And sample mean, which is p n1 or directly x bar is there. Sorry. Okay. So we now equate expected value of x to m1. This implies theta by 2 is equal to x bar. So theta cap is nothing but twice of x bar. Okay. So if since we have not discussing the maximum likelihood estimate, but for the purpose only, the theta cap MLE is actually xn. Xn is nothing but maximum of xi. Okay. So the la greatest ordered observation, the maximum ordered observation is this. So this is the MLE of theta, and this is the 2x bar, twice of the sample mean is the method of moment estimator for the parameter theta. Okay, so this is how we are able to solve. If, for example, if we have different if we have different functional form, then again we will use the different like the same approach, and then calculation is like somewhat lengthy. like uh, if we are given fx equal to uniform alpha beta, x is a uniform alpha beta distribution, then in that case again first order derivative and the second, sorry, first order moment and second order population moments are calculated, and then the first order sample moment and the second order sample moment is also going to calculate, we will calculate this and then equate them and solve them for the two parameters, and we have the different moment estimator. And for the similar case, for the maximum likelihood estimator, we will perform the, we will construct the likelihood function, then log likelihood function, then differentiate, partially differentiate that log likelihood function with respect to the two parameters, and then equate them to zero. We are able to calculate the this. Okay, but you will find one mistake actually. That's why I am telling this. In case of normal, in case of uniform distribution, we are not able to estimate the maximum likelihood estimator with the this method only. So we have some different approach there. Okay, we directly using the functional form. Okay, then with the help of the functional form, we are able to find out for which value of those sample values the parameter is maximized, the functional value is maximized, and those functional values are nothing but the maximum likelihood estimate. That we will discuss in further classes if there is classes. And if you people have any doubt, we will definitely solve this. Like here only, if you can see, if you can see this this MLE is not calculated with the help of the method we have discussed above. Okay, if you are using the above likelihood function, log likelihood function, that differentiate with respect to the parameter and equate it to zero, then you will find an absurd result actually. Okay, so this MLE is not calculated with the help of the usual method that we have discussed above. Okay, so we have different approaches as well for the estimation purpose. We will discuss in later classes, obviously. Okay, so if anyone have any doubt up to this point, then he or she may ask. If not, then we should conclude our session here. So anyone?
No, sir.
Okay. Okay, let me then stop the recording first.